Alright, so this is the integral. These are the integrals that we evaluated. We got results for everyone, for each of them. And well, so let's continue to the end, to the final result, by just putting everything together. So the result of the first integral, so coming back to the original integral, that's 1/2 ln of x squared plus 4. And again, in this case, no need for absolute value bars because x squared plus 4 is always positive. So no need for them. Plus the value of the second integral. So let me go back to the value of the second integral. The value is 1/2 arctan of x over 2. So let's put that together. So plus 1/2 arctan of x over 2. Now, for the remaining two integrals, 3 and 4, notice in this case we needed a couple of factors of -4. I also mentioned last time that I was going to skip those factors and just put them back in when we put everything together. So notice when we evaluated those integrals the other day, we didn't include those -4 just to avoid having too many constants and too many factors individually. So let's just include them now. So that's going to be -4 times with the result of the third integral, which in this case is what was that here? That's 1/2 times x squared plus 4. Okay, and finally -4 times the result of what we got for the last integral, that the one that we used, what was that, a trigonometric substitution, so which is these two terms right here. So 1/16 arctan of x over 2 plus x over 8 over x squared plus 4. And then, well, this is the part where we put the plus c to begin. So the remaining part of this problem, well, it's just to combine like terms. In this case, we will do some of them and reduce any constants here. For example, this -4 reduces with a 2, leaving us with a 2 and a 1. And over here, this 4/16 reduces to leave us with a 1 and a 4, and same over here, another 1 and a 2. So let's put them together. So the first two terms remain the same. 1/2 ln x squared plus 4 plus 1/2 arctan x over 2 minus 2 over x squared plus 4 and minus 1/4 arctan x over 2 and minus, because negative times a positive is negative, and 1/2, that's another 1/2 x over x squared plus 4 plus c. Well, it turns out that we can combine like terms because we have these arctans that have the same argument inside of their parentheses. They have the same composition. All they have difference is their coefficient. So all we do is subtract 1/4 from a half, leaving us with actually 1/4. The remaining terms remain the same. And minus 2 over x squared plus 4 and plus x. And I'm going to write, instead of a half, I'm going to write it as 2 times x squared plus 4 plus c. This would be our final answer. This would be the end of this section 7.4. Now, if you wonder if you will ever get anything this crazy on an exam or a quiz, well, think about the amount of time it took us to go over this exercise. That's actually pretty much the whole last lecture, and we still needed one more lecture to finish it up. So you know you're not going to get anything this crazy. But the reason I like going over an example like this particular This particular one is because it puts together all the use substitutions, other trigonometric, other integration techniques, like things that you learned back in College 1, and then what else did we review? Trigonometric integration along with trigonometric substitution. This way it remains fresh all the time, right? So, question?
Shouldn't that be minus x over 2 x squared plus 4? Just rather minus.
Yes, this one, right?
Yeah.
Yep, I forgot that minus. Oh yeah, this minus right here. Thank you. Alright. Well, in the meantime, so let's move on to a next section. So today, we're going to jump all the way from 7.4 to 7.8. All the sections in between are are not part of what we're supposed to cover in the course. Those deal with evaluating integrals using other weird substitution and other weird methods. Also numerical methods such as the Simpson's rule, the trapezoid rule, which we don't cover. You'll cover those when you take numerical methods in your engineering courses or science or other science courses, and integration using a table of formulas, which we're not going to do as well. In the meantime, what we're going to do then is do what we call improper integrals. And there's two types of improper integrals. We're going to discuss both. In fact, type 1 integrals are subdivided, if you will, into three different cases. Well, we're going to look at examples of each case, but the way we're going to go about notation for improper integrals, it's going to be slightly different than the way we go about the regular integrals. Well, so type 1 integrals, those integrals are when we have infinite limits. That is, when we integrate from a number to positive infinity, or when we integrate from negative infinity to some number. Well, so here is the issue here. Okay, coming back to the definition of the integral. So we have this integral from a to b. Ultimately, the integral of f of x from a to b, that's going to give us the area under the curve. And the way we go about it, when we integrate little f, that's going to be big F, evaluated from a to b, and we do a big F of big F of b minus big F of a. So we just evaluate at the upper limit, evaluate the antiderivative of the upper limit minus evaluate at the lower limit. That's what we have been doing since somewhat the end of Calculus 1 and throughout the semester in this course. We apply this to find areas below curves, between curves, surface, not yet, surface area. Actually we did. Volumes of solids of revolution. So you know the drill for this, all right? Well, so when it comes to evaluating an integral, an improper integral, having one of the limits being infinity, there is an issue with the way we go about the notation. We cannot just go like this. The integral from a to infinity of little f, that's supposed to be big F. Well, essentially is big F. Evaluate from a to infinity, and then use the fundamental theorem, f of infinity minus f of a. Well, that's not, unfortunately, what we are supposed to do. Even though when we evaluate these limits, yes, technically we're substituting the upper limit minus the lower limit, but there is an issue with this notation. We cannot treat infinity like a number because, well, infinity, it's just a symbol, it's just an idea of something that never ends, just gets big, big, and big, and until blowing up to something that never ends. So we cannot do arithmetic operations with something we don't know how big it is minus a number. Technically, I mean, it's something big. Minus 1, well, it's still big. Or minus minus 7, it's still big, you know? But we don't do arithmetic with infinity symbols. In some cases it's needed, but I mean it's like not so in general that's not what we're going to do in this case. So for this reason we will turn the function problem into a limit problem. Again, recall that what we're doing here is evaluating functions. When you evaluate a function, there are two possible outcomes. Number one, the function is defined, or number two, the function is undefined. When it comes to limits, there's also two possible outcomes. Number one, the limit exists or the limit does not exist. Okay, so but what's the value of a function representing? So for example, if I have f of 3 equals to 5, well, when we define the value of a function, we're answering the question whether we can stand at that point. So when I move 3 units in the x direction, I'm getting to 5 units in the y direction, and I stand at that point. That's not what a limit is. The idea of a limit is where are we getting to in the y direction as we get closer and closer to certain value of x. So even though, yes, when we compute limits, we plug in values, that is exactly the same as evaluating function, but the fact that we have some limit notation, that means that we're getting a different idea about it essentially, but algebraically it's exactly the same. Okay, so in this case, when we integrate from a to b, where b is the upper limit being infinity, we turn this into a limit problem. Everything else will be exactly the same. So the way we will evaluate the integrals, same rules, no new methods, no new rules, same general power rule by parts, partial fractions, etc. And when it comes to computing the limits, same limit rules, no new rules, possibly even L'Hopital's rule if necessary, but I think it's going to be very straightforward. Now, well, what about the results of these integrals? Well, number one, so we will evaluate an integral via evaluating a limit. So if the limit exists, we say that the integral converges. But otherwise, if the limit blows up to infinity or is z and e, well, the integral is divergent. So we're going to have a look at different examples in different situations to see this in action. Okay, so number one. Example number one, letter A, the integral from 1 to infinity of 1 over x squared with respect x. So number one, we need to change this into a limit problem with b approaching infinity and the integral from 1 to b. And at the same time, I'm going to move this x squared that it's in the denominator to the numerator so we can integrate, because in this position we can't just integrate that. So we're ready to integrate this. So this will be a limit as b approaches infinity. Well, what's the integral of x to the negative 2? So add 1 to the exponent and divide by the new exponent you obtain. In this case, isn't that x to the negative 1 over negative 1? And we evaluate this from 1 to b. So number one, before we do the fundamental theorem of calculus, well, how about we get this negative in front of the limit, so we don't have to deal with too many negatives when we do the calculations here. Also, I'm going to write this x to the negative 1 as 1 over x, and then 1 over, well, actually with limits first, and then we're good to go. F of b minus f of a that's 1 over b minus 1 over 1. Well, so in this case we compute the limit. Notice we're not evaluating a function. We're not looking whether we can stand at that point. We're finding a limit. Okay, so number one, where is this limit gonna go? 0. So that's gonna be then negative So once we evaluate the limit, we no longer write this limit symbol. So this is negative 0 minus 1 over 1, which is 1, which results into a 1. And well, what did we get over here? We got a finite number, a finite value. That means the limit exists. And because the limit exists, the integral converges. All right, the integral converges. Let's see what we get for the next example. Let's see if it's the same case. Will it converge? Will it diverge? Well, we'll see. So number one, we have another integral, another improper integral that first of all we need to rewrite it as a limit problem. In this case, we are going to change that upper limit of infinity as a b, and then redefine this as a limit having b approaching 1. And well, I'm going to write this 1 over the square root of x first as 1 over x to the 1/2, and then I'm going to move this x to the 1/2 in the denominator as an x to the negative 1/2 in the numerator, so we can integrate, because just like this we can't integrate it. So, well, the integral of x to the negative 1/2, what do we do? Add 1 to the exponent and then divide by whatever we get from adding 1 to that exponent. So that's still limit b approaching 1 of x to the negative 1/2 plus 1, isn't that a 1/2? And divide by 1/2. Evaluate this from 1 to b. Okay, let's do a couple of things here. Number one, you don't want this weird looking fraction right here, so recall that whenever we divide. Yes?
Why are we going from, why is b going to 9?
Oh, no. It's supposed to be infinity. Thank you. Yes. So, instead of dividing by a fraction, we're going to multiply by the reciprocal, and the reciprocal of 1/2 is going to be 2. But that constant, that factor, I'd rather have it outside of the limit, so we don't have to deal with so many constants when evaluating the limit. So that's the number one thing we're going to do. Take out the constant, be approaching infinity, and I'm going to change this x to the 1/2 as a radical. Square root of x from 1 to b. Alright, so the rest of the problem, well, number one is fundamental theorem of calculus, that is f of upper limit minus f of lower limit. And so that's the square root of b minus the square root of 1. Okay, so we need to compute this limit. So where is this square root of b going to go for large values of b? Infinity. So what are we going to get? Infinity minus the square root of 1, which is just 1. Well, that's not going to do any harm to the infinity, right? And then on top of that, multiply that by 2. It's still going to get bigger and bigger, twice as big. Just call it big. How big? Well, just infinity. Well, in this case, the limit does not exist. The limit is infinity. So, for this reason, the integral diverges. Alright, the integral diverges in this case. Alright? So one example of it, how we treat it, well, limit problem, integrate, fundamental theorem of calculus, compute the limit. Okay. Let's look at the second case for improper integrals of type 1. So in a similar way that we integrate from some value to b, this time we're going to integrate towards a negative infinity. Question?
In this problem, that go from
This one? Well, so if we have, for example, if we look at the graph of square root of x, and that's going to look like this. And that's simply just going to go all the way to infinity for large values. And then, well, so infinity minus 1, well, it's still going to be infinity. And then on top of that, keep multiplying by 2, well, that's still infinity. So again, we really don't do arithmetic operations with infinity. So even if that infinity gets multiplied by 2 or exponentiated by some base, it's still getting big, and we just represent it as infinity. Right? So for the second case, in which this time the lower limit of integration is negative infinity, so when we evaluate definite integrals, our generic form is to integrate from a to b. So in this case, because our lower limit is negative infinity, we are going to define this in terms of a limit, but in this case going from a to negative infinity, or rather approaching a to negative infinity. And well, everything else will be the same. If we get a finite value, the limit exists, the integral converges. But otherwise, if the limit is the final answer to the limit is infinity or d&e, well, then the integral is said to be divergent. All right. So let's see. So number one, let's look at a couple of examples. So what do we have? The integral from negative infinity to positive 3. And well, how about we change this into a limit problem? Limit from not b approaching infinity, but this time a approaching negative infinity. And so that's going to go from a to 3. In this case, I'm not going to integrate x to the 4 in the denominator, so we need to have that x to the negative 4 with respect x. And well, let's compute the integral first. So that's a limit. We still have a limit. And the integral of x to the negative 4, that's add 1 to the exponent. Isn't that x to the negative 3? Over negative 3, evaluated from a to 3. Well, again, in a similar way that we did with the previous couple of examples, okay, this negative 3 that we have in the denominator, how about we write it outside as a negative 1/3? Again, to avoid too many factors when it comes to the calculation with the upper and lower limit. And then secondly, let's write this x to the negative 3 as 1 over x cubed. This evaluated from a to 3. So, this will be negative 1/3 limit of 1 over 3 cubed minus 1 over a cubed as a approaches negative infinity. Now the question is, when we evaluate the limit, where is this term going to go to? Negative infinity? 0, right? Because we're dividing by really big number, so we get nothing. So well, that's going to be negative 1/3 limit. Oh no, not limit anymore. So that's going to be 1 over 3 cubed, that's 1 over 27, minus 0. And when we multiply these two numbers, that should give us negative 1 over 81. And again, because we got a finite number, a finite value, the limit exists. And question?
Earlier it said that if f is continuous for the range, we can
Do you know what? I just realized that at the beginning when I did this problem, because it's not continuous at 0, right? So let's do the following. To fix this issue, how about we integrate to negative 3 instead? And so that's going to be negative 3, negative 3, negative 3. That's going to be negative 1 over 27, giving us a positive 1 over 81. So that must be a lot better in this case. Thank you for that. And then, well, for this reason, because our limit, it's a finite value, the integral converges. All right. All right, let's have a look at this one. So number one, what do we have? We have the integral of an exponential function whose exponent is negative. And well, the profile for this function looks like this, you know. So it's because of the negative exponent that represents some sort of decay. So as we go from 0 to really large values of x, well, it's getting smaller and smaller. So at first glance, this might be the case in which the integral converges, right? However, we need to be very careful about the direction of infinity that we are working with in this case, because we're not integrating towards positive infinity. In this case, we are integrating from negative infinity to 4. So actually, this area gets infinitely big towards the left. So, well, this picture should depict something that diverges, something that blows up to infinity. Now, let's verify that with the by working on the integral. So number one, limit as a, not b, approaching negative infinity, the integral from a to 4. Let me take the 8 outside of the integral, e to the negative 5x. That's equal to 8. I'm going to leave a space for something here. Limit a approaching negative infinity. What's the integral of e to the negative 5x? Number one, it's itself, and times 1/5, negative 1/5. If we were differentiating this, it would be times negative 5. But we're integrating negative 1/5. I'm going to write it outside of the integral. And that goes from a to 4. So negative 8/5 limit as a approaches negative infinity of e to the negative 5 times 4 minus e to the negative a. Alright? And well, number one, where is this limit going to go to? Be careful with the signs in here. Infinity? Okay. So technically, I mean, if we were to do like the arithmetic, so the arithmetics with infinity only work when we're multiplying opposite signs, or we're multiplying signs. For example, we would have done negative e to the negative times negative infinity. Alright, and what is this going to be? So becomes positive, right? And well, so e to the infinity, well, it's still big, so this goes to infinity, and it doesn't matter what the remaining terms are. This is simply going to blow up to infinity. And for this reason, we say that the integral diverges. Alright. Those are the two cases. Yes? Oh, yes, e to the 5a. That's true. Thank you. E to the negative 5a. And in the end, well, that's going to be still negative infinity times negative infinity times negative is going to be positive bit. Yes? Oh, yes, because of this sign right here, right? So, oh, wait, no, that's fine, because negative times the negative outside, it becomes positive. All Alright, those were the two separate cases, integrating to positive infinity and then integrating from negative infinity. Now let's do the third case, in which we will integrate from negative infinity to positive infinity. Alright, and well, the picture, it's pretty much putting them together. We're integrating from, we're getting this infinite area all the way to positive, from negative infinity to positive infinity. But in this case, we need to split this integral into two. The most common case is to split the integral, like let's call this, for instance, I1, which is the integral from negative infinity to 0. And then let's call this I2, which is the integral from 0 all the way to positive infinity. And well, should be 0 always that center value? Not necessarily. There are cases in which we may need to change that center value to a 4, a 5. Well, that depending on the case. All right. So well, and again, so we compute this integral. And if we get a finite value, the limit exists, that means the integral converges. But otherwise, if we get a limit equal to infinity or does not exist, the integral is said to diverge. Okay? Same idea. Now, let's have a look at this integral. So how about we split this integral into two separate integrals? Number one, I'm going to label lower limit as an a approaching negative from at a approaches negative infinity of the integral from a, and I'm gonna go to 0. It's gonna be the first integral, 1 over 1 plus x squared dx, plus the second part, limit, in this case b approaching infinity, the integral from a, no, not from a, actually from 0 to b, 1 over 1 plus x squared dx. Alright, well, notice that the integral that we're going to evaluate is the same, so no need to look for two different methods of integration. Number one, any ideas on how to compute this integral, the integral of 1 over 1 plus x squared? It's the arctangent rule, right? Because u substitution, it's definitely not going to work. If you check this out, I mean, let me just do it real quick. So u equals 1 plus x squared, du equals to x dx. Well, nothing wrong with this, except that we're missing a factor of x in the numerator in a way that the u du setup or setting works. So in this case, it's not the case, unfortunately. So we need to use another rule, that is the arctangent rule. So on the one hand, we're going to obtain the limit as a approaches negative infinity of arctan x evaluated from a to 0 plus the limit as b approaches infinity of arctangent of x from 0 to b. So let's use the fundamental theorem of calculus individually for each term in this case. So number one, well, we still stick to the limit notation. Limit a approaches negative infinity, and the upper limit, which is 0, that's arctangent of 0 minus arctangent of a, plus, let's do the same with the second expression, with the second term involving the limit as b approaches positive infinity. So that will be limit b approaches infinity, and that's upper limit, which is b, arctan of b minus arctan of 0. Alright, well, let's do one thing at a time. How about we evaluate the arctangent of 0? What's arctangent of 0? In other words, what angle has a tangent equal to 0? 0. Alright, thank you. Thank you. So 0, and that one also goes to 0. The other question is, and this one might be a little tricky, what's arctangent at negative infinity and arctangent at infinity? Will it be infinity, blow up to infinity, and the integral blows up because it looks like infinity?
It's still 0.
Not 0. Yes. Pi over 2. And, well, negative pi over 2 for the negative case. Well, how about we do the pre-calculus of that? I could give you the answer and just call it a day, but I think it's worth to go back and see where is this coming from. So number 1, let's consider the graph of the arctangent function. We know this graph looks like this, right? So, and the most important thing here is the labels for the asymptotes. That's a negative pi over 2, pi over 2, 3 pi over 2. So we have these vertical asymptotes on the graph of the tangent function at all odd multiples of pi over 2. The next one would be 5 pi over 2, 7 pi over 2, 9 pi over 2, and on the negative side, negative 3 pi over 2, negative 5 pi over 2, etc. Well, so this arctangent function really means the inverse tangent function. But well, before defining the inverse tangent function, we need to determine whether the original function, the tangent function, is invertible. In other words, we need to determine whether the tangent function is 1-to-1. Well, the easiest way to go about it is by looking at its graph and do the horizontal line test. And do you see the problem here? It's failing the horizontal line test. So at first glance, the tangent function is not an invertible function. However, there's something to do the trick. And this would be by restricting the domain of the tangent function. That is restricted to be only from negative pi over 2 to pi over 2. And if we forget about the rest of the graph, let's do the horizontal line test, and this time passes the horizontal line test but only if we restrict the domain here. Okay, so that means that when we define the inverse tangent function, well, f inverse of x, well, this should look like this, with the horizontal asymptotes here. So those vertical asymptotes that we had here, when we get the inverse function, those become horizontal asymptotes. And well, and those horizontal asymptotes are going to be at the same values that they came from x, from the world of x towards the world of y. But these ones are going to be negative pi over 2 to pi over 2. Now, let's evaluate the limit for arctangent when a equals infinity. Well, from the graph is easier because, well, what's going to happen? So all we're doing is approaching asymptotically from the top, towards the top to pi over 2. In this case, this one is going to go to pi over 2. And let's do the same on the negative side. We're going to get close, but asymptotically, to negative pi over 2. So that's negative pi over 2. Well, I think we have all the information that we need in order to get the final answer for this. So this will be then, careful, negative, we have a negative in the front, negative times negative pi over 2, isn't that a pi over 2? Plus pi over 2 And in this case, final answer, pi. And because the limit is finite, this means that the integral converges and converges to pi. Right? Yes, it might have been a while since you saw this relation between the tangent and the arctangent and all the implications of restricting the domain and all that, but it's always good to go back and see where it is coming from rather than just giving this final answer. Of course, you don't have to explain all this if you're giving this integral on a quiz or an exam. I mean, at this point, it's understood that you know where is this coming from and you know why arctangent of infinity is.